Okay, this is the agenda for my presentation today. We are going to go through this project by looking over what is VGA, how it works, we will learn what is Xilinx MicroBlaze, then we will go over to see what my project is doing, yes, hardware and software design, then I will demonstration my project. After that, I will discuss what the future development that we can do to improve it and to make it better. First review what is VGA. VGA, which is stand for Video Graphic Array, and is defined by Visa organization. It uses a 15-pin connector to transmit RGB color signal and it supports various resolution, but it typically operates at 640 times 480 resolution. As you can see from the VGA connector diagram below, we only concentrate on the 5 signal out of 15 pin in this project. These 5 main VGA signals are red, green, blue, HS, and VS. The red, green, and blue are 3 analog signals that specify the color of a point on the screen, which will be based on the RGB signal intensity, while horizontal and vertical sync signal provide a positional reference of where the point should be displayed on the screen. By properly driving these 5 signals according to the VGA timing certification, which we will discuss later in next slide, we can display everything we want on any VGA monitor. This is the timing specification for 640 by 480 resolution at 60 Hz. Firstly, the VGA controller generates horizontal or vertical sync paths and manage video data based on the path clock generated by a clock divider. This is fundamental for displaying objects on the VGA screen, as it ensures proper standardization and timing. Horizontal sync paths indicate the start of each new line, while vertical sync paths mark the beginning of each frame. Together with push interval, this signal enables stable and clear image rendering. Following this certification ensures that VGA controller is compatible with various devices and it enables smooth display output on the VGA screen. You might be asking, what is the Xilinx MicroBlaze and why do we use it on your project? MicroBlaze is a 3264-bit soft processor core designed for Xilinx FPGA. Here's a close look. Unlike traditional processors, which are hardwired into the physical hardware, MicroBlaze is standardized into a FPGA as a soft processor core. This unique feature makes it highly configurable, allowing for customization to meet specific application requirements. Similar to the other IP core, MicroBlaze can be easily set out and integrate into the block design of the FPGA. MicroBlaze architecture offers user extensive configurability options. Users can adjust parameters such as industrial set architecture, test design, and the other portfolio. This level of flexibility enables customization for a wide range of tests and applications. Moreover, MicroBlaze comes with built-in support for access bus standard. This ensures seamless data transfer between different IP cores, which are enhancing the overall system efficiency. Additionally, MicroBlaze is cost-effective and easy of standardized into the FPGA, which makes it an attractive choice for developers looking to implement customized processor solution. Here's the overview of my project application. This project leverages the MicroBlaze processor core to manage software tests. These tests include real-time data processing, control function, and interfacing with hardware device connected to the VGA monitor. By utilizing the MicroBlaze core, the application can efficiently handle user input for interface like button or switch, and then generate the necessary output signal for the VGA display. This seamless integration between software and hardware components enhances user interaction, allowing for various applications such as displaying a digital clock on the VGA screen. Overall, the project aims to develop a comprehensive VGA-based application that showcases the capability of MicroBlaze processor while enhancing user interaction through the VGA display. Moving on to the hardware setup, I use Xilinx Vivado and IP integrator in the block diagram design to assemble the components. The main central process CPU in this design is a MicroBlaze soft core processor, which handles most of the tasks. Our board supports DDR3 memory, which acts as the external memory for storing data. For the display output, I connect VGA monitor to the VGA port on board. To available user interaction, I integrate push button and a slide switch for timekeeping setting. This this allows user to adjust the time and date as needed. The MicroBlaze processor effectively manages all these functions. The images are displayed using a fan buffer installed in the DDR memory, which ensures smooth visual display. To signal data transfer, I implement the delay memory access for the VGA output. This setup, coupled with Xilinx IP and S-Bus protocol, ensure reliable performance and user-friendly operation. Okay, so this is the hardware block design, which I designed in the Xilinx Vivado. From the left to the right, we have the clock vessel, which allow me to use the onboard 100 MHz clock to generate the different current that are going to feed the rest of the system. In addition to that, we have the FPGA CPU reset that allow us to use the CPU reset button to control where we reset the microBlaze or where we need to reset the other device we connect. Next, we can see the microBlaze is on the center here with our DDR memory connect to the right of the microBlaze and the SD RAM on the top of the top right corner. After that, we have the access connect interconnect that allow the microBlaze to talk to the and share information with all of the other device. Now we have the UR, USB UR, button, LED, switch, also the VGA. This is the top level view of the overall system bar diagram I create for this project. It provides a clear and easy to understand overview of the system architecture. Starting from the left, we have the Xilinx processor servicing as the main CPU. Between the MicroBlaze processor and all the other device, we have the asset interconnect between them to allow the main CPU to communicate data with them. This includes the memory interface generator, which access the data stored in the DDR memory. Additionally, There's the USB UART serial port for serial communication and debugging purpose. I also use the onboard LED switch and push button GPIO to available in user interaction for time and date adjustment. To manage user input infinity, an interlock controller is connected to the push button GPIO. It detects button status change and generate interlock signal accordingly. When a button is pushed or the plus is detected, the interlock controller sends an interlock request to the processor, allow the processor to identify specific button is pushed based on the received interlock. Lastly, we have the VGA output IP module, which we will discuss in detail in future slide. While implementing VGA output for the Nexys A7 GPIO board to be controlled by the MicroBlaze, I encountered a challenge. Fortunately, I found a solution in an existing VGA IP library originally designed for Jumbo board, so I chose to use this library as a reference design. And I successfully converted the VGA functionality from the Jumbo to the Nexys A7 and integrate it with the MicroBlaze. This IP library utilizes the onboard GPI, the onboard VGA connector to provide a 16-bit per pixel display output. Then the VGA output uses the Nexys video DMA IP module code to directly copy frame buffer data stored in the DDR memory and then display it on the VGA screen, which is also generating VGA color and signal while in the process. For this slide, I'm going to walk through the hardware bar design in Vivado. So this is the bar design I designed in the Vivado. As we discussed in the previous hardware design slide, we have the clock bezel for our 100 MHz onboard clock. Then we have the MicroBlaze in the center. To the right of the MicroBlaze, we have the DDR memory used to read or store data on the DDR. After that, we have the device connect on board, have the button, USB UART, VGA, LED, and switch, which all connect through the access interconnect. Now, after that, we have the address editor. This is automated generated by the block design for the address in the MicroBlaze. Here's the address mapping of the different device we connect. Now here's the LED switch button and UART and so on. Next has the concentrate. On here, I just define the voltage for the clock, but I did not define the information for the switch and LED as it automated will be created uh, by the design. So in here I have the GPIO button I just select here to be a push button. Then it will be automated generate a counter file for this button. Or you can just drag and drop from the board menu to the toolbar here. Then it will be created. Yeah. Then yeah, here's mostly my block design. After I got a synthesized run a synthesized implementation and generate a bit screen and can export it to the hardware. Then it will be include a bit string. Then we will do the software side later. Okay. So we have our hardware design on the FPGA ready set up. Next, we will need to write a C program for the MicroBlaze processor to display digital clock on the VGA monitor. First, we need to use Latest IDE, which was known as Xilinx SDK prior to 2019. In Vivado, we need to export our hardware design with bitstream and save it to the local drive. Then we import this hardware design into Latest. To run the Latest, we can go to Vivado, select Tool menu, and select Launch Latest IDE. Next, we need to create a new application project and select the hardware platform that we just create from the Vivado. And it will generate a board support package. From there, we just need to write our C or C++ program on how we want to display the digital clock on the VGA screen, such as time, hour, minute, and second, and a day. Finally, after we finish coding, we can compile the BSP and link to it to have all our driver then download our program to the FPGA to see it's displaying the clock on the VGA monitor. This is the digital clock time setting instruction for adjusting the clock time and date. To adjust the digital clock time, first we toggle the switch 0 to on position. This is available in the time setting mode. Press the center push button to reset the clock time to 00. Use the out push button to increase the time, the down push button to decrease the time. To switch between the different time units, like second, minute, and hour, we just press the left push button or right push button. Once the desired time is set, toggle the switch 0 back to off position to resume normal clock operation on the VGA monitor. To adjust the digital clock date, toggle the switch 1 to on position. This activates the date setting mode. Press the center push button to reset the clock date to January 1st, 2024. Use the out push button to increase the date, and down push button to increase it. To switch between the different day units, like day, month, and year, press the left push button or right push button. Once the desired date is made, toggle the switch 1 back to the off position to resume the normal clock operation on the VGA monitor. For this slide, we are going to walk through the project creation, BSP generation in Vortex IDE, and take a review of my C programming language and how it's run on the VGA monitor. Alright, let's go here. First, we need to export the hardware platform. Go through that. After that, we need to go to the tool menu and select the launch Vortex IDE to launch the IDE. Now we need to select the workspace for our workspace. Now, in next step, we just need to create a new application project. Now we need to select the new platform for our project. Now we'll give it the application name. We can choose any template. I can choose the hello world. That's how we create a application project on the widgets. Um, so since I already created a project for myself, so I'm going to just use my own project. So here's my project. So in here I have my main file in here. So here's just the include the header file. Here's a constant definition. This all the for mouse initialize the GPIO for the LED switch and push button. Here's the interrupt for the push button initialization. Here's the display how to display the time and date. And this is a function to handle the button plus for time. That's the other function for button, how to handle the button pass for the date. So we have the button out for increasing the date and button down to decrease the date. If it's the left or right to select different date union. Here's a time setting. If the switch is switch 0 is high, then we do the setting for the time. If switch value is 1, then we'll do the setting for the date. If both are low, there's no setting, so we're just doing a normal operation for the time. Here's the main function. So we can just compile and build a project. It's no error, so I can just download it to my board. Now it will be programming. I will see it on my board. It's showing the time. I will show it on the last demo last night. Thank you.
Okay, so this is how I set up for my final project using the Nexys A7 FPGA development board. Using the onboard VGA connect to the VGA monitor for the digital clock project. So in here, the time, the clock is running as normal. When I switch the switch 0, the time is stop running. Now I can change the setting. So for the up button is for increase the time, and down button is decrease the time, and left and right is switch the time unit, and center button is reset the time to 0. So right now I can I try to increase the time. You see the time increase. I'm trying to do the decrease the time. Decrease. I can also change the unit. I can go to the left. It will be changed to from the second to minute. No, I increase the minute. I increase it. I push the down button. It decrease the minute. I can also do the set. Pull the switch 1 to high. I can change the date. The May 1st. I can also decrease the time. I can also change the month. So if it's over the month is over in December, it will be go to this year. I can also go back to the date. If I push the center button, it will be reset the month to January 1st, 2024. Same for the time. If you push the center button, it will be reset the time to 00 for the time. So if I make it go slow, it will be go back to normal. So yeah, so this is my demo for the digital clock time keeping. Thank you.
For future development, we can enhance the functionality by integrating an alarm feature. This could allow user to set alarm time using a button or switch. The system could then compare the current time with the set alarm time and trigger the alarm signal when they match. Additionally, we can utilize the onboard 7-segment display to show the certain time and date, providing user with visual feedback. To improve accuracy, we can connect the Nexys board to the internet using the onboard internet connector to get a real-time data from the online source. So this is my presentation today. Thank you for watching.